So a computer was
It's my great pleasure to introduce Professor Gil Refael from Caltech. Gil actually got his PhD with Daniel Fisher and with Eugene back when Daniel was at Harvard and was a Kitaev fellow before starting at Caltech. Gil has really done seminal work on a number of topics, from studying topological phases to driven entropy systems to disordered systems and many-body localization. And as a PhD student, I was really inspired by many of Gil's papers, and I continue to be. Now, more recently, Gil has been thinking more about error correction, and today he'll be telling us about GKP codes.
Thanks, Radhika. Thanks for the lovely introduction. I'm blushing.
Oh, and all sorts of awards for that.
It's already spent. They're spent. It's fine. Anyway, it's really a pleasure to be here. Thank you, Radhika, for organizing this visit, and all of you who I met over the last 2 days for making it really enjoyable. Okay, so I'm going to talk about something that's a little bit outside my traditional expertise, bosonic codes for quantum information. So this is going to be about GKP codes, which are like the gold standard for bosonic error correcting codes. I'll try to give you a bit of the basics and as much as time allows, show you about all the natural gates that we can do in the dissipative realization that we're doing. But I guess the first thing that I should really do is thank the people who actually did the work. And these are Frederick Nathan, who was a postdoc at Caltech, then became the Carlsberg Fellow in Copenhagen, and told us all about the history of that fellowship, which was also given to Niels Bohr at some point. So I don't know if you heard the story of Bohr having like a beer tap in his home. So I heard it as an undergraduate, and I thought, gee, we really love beer. But then what Frederick tells us is that actually, because his home was in the brewery, it's part of the fellowship. So Frederick and Liam, a student at Caltech, were leading the charge on this. And this was done in collaboration with our partners in crime in the Amazon CQC, Kyungshu, Arna, Matt, and also in Chicago. Okay, so I don't think I have so much material, so feel free to interrupt me anytime with questions. I will try to make it as simple as I can. And actually, it's very simple, so it's not very hard to make it simple. Okay, so we'll start with talking about GKP codes. What are they? I'll push a circuit realization on you, and then show you how to do gates in a native way in this architecture, and how to do readout. And if I have time, I can tell you a few words about also having T-gates, like pretty good T-gates that can appear in this realization. That's very recent work, so we'll see how well I can do that. Okay, so basics of quantum information. You need a qubit. Qubit has 2 states. If it's a spin, it could be like up and down. You want to keep the quantum information in the up and downness, also in the relative phase between those 2 states when they're in superposition. Big problem is like quantum systems are pretty fragile. So if you have a spin flip, say you go from 1 to 0, it happens easily, then you lose all quantum information. You can't deal with it. So there's a big industry in trying to find out ways of encoding quantum information into 2-level systems, into effective 2-level systems in a way that's robust, such that the information does not get lost very easily to matrix elements or something like that, 0, etc. And the most celebrated, I would say, suggestion came from Gottesman, Preskill, and Kitaev. This is the GKP code. And the idea was, take a bosonic degree of freedom. Think about an harmonic oscillator, but no Hamiltonian for them. The bosonic degree of freedom, x and p. The x, you can, and what they said, take the x coordinate and code the qubit into a periodic structure in x. Namely, if you want a 0 state, put it in like odd wells of some imaginary potential, by imaginary, something that's imagined, not something that multiplies by I. And if you want one qubit, one state, then you put it in the odd wells. And the idea was that if you can put the wave function into narrow slivers of this periodic structure, even if the wave function kind of diffuses away, we can always do something to correct it without losing the quantum information. So that's the rough thing, but here's a more beefed up introduction to this. So what they said is you should have two stabilizers, two operators, where the state of the system gives you one upon operation of those operators. One operator would be e to the I phi. So I'm using phi and q for location and momentum for reasons that will become obvious, probably are obvious already from the introduction. So e to the I phi, phi is an angle, has 2 pi periodicity. This operator will be 1 if phi is 0, 2 pi, 4 pi, minus 2 pi, minus 4 pi, etc. We want that operator to park our state in the eigenvalue 1 subspace. And then we'll write another operator that's pretty much identical, but for charge, for momentum. So if the momentum operator is like 1 over I dd phi, this is the I, it's imaginary. So now we are plugging it in. 1 over I dd phi, this operator is a translation operator in phi space by 4 pi. So if you operate that to the wave function, it'll take whatever weight you have here and pass it over 4 pi forward, etc. So it doesn't mix odd and even wells, but it localizes things over wells of the same parity. Now, phi and q have a commutation relation, right? Momentum location. You should not be able to have states that diagonalize both simultaneously, don't commute. However, this operator and that operator do commute. Kind of like this magic, if you apply this operator to that, you just translate phi by 4 pi, well, e to the I 4 pi is 1 pi. So that means that those operators can commute, and you could actually have states that are simultaneous eigenstates for both operators. And that was the key to John's proposal and the beginning of this collaboration that gave these states. So the encoding under such a qubit would be a 0 and 1 state that lies in the even for 0 and in the odd wells for 1. So if you wish, there's an SZ operator for this, which looks like this stabilizer curve. Right, so if you have your state is a 2 pi, 6 pi, etc., that over 2 gives you some 2 pi's plus pi. It'll give you a minus 1 of this. And if you're in the odd well, so even wells, just get 1. Now I would like to complain a bit. I mean, people who know me well know that I complain quite often. So, truth in advertising. So I read about GKT codes several times, but I keep hearing, we keep hearing about this at some regularity. And you feel bad when you hear about something and you don't know what it is. I would go, what's my regularity or I don't want to get into that. It was not super regular, but it could be regular, but it's regularizable.
No, we're not talking about anything anymore. We're just saying words.
Yeah, now it occurs to me that I sounded released for a recording. So. Yeah, so I would look at the paper. The paper didn't have this algebra. The paper has an algebra that has square root of pi here and square root of pi here. Of course, it's the same for the mathematically minded, but people like me who look at this and don't exactly know what they're looking at, look at square root of pi and wonder where you get square root of pi anywhere. And so I would learn it, know it, forget it, and do that with some regularity. And at some point, I got frustrated with my inability to remember this. So I was trying to understand, what is this? And here's what occurred to me. That actually, what this is talking about is a torsional pendulum. So I told you, atomic degree of freedom, right, x and t. Let's make it an angle, and fine. Actually, the system that we should have in mind is a torsional pendulum. So I don't know, some of you saw the Grandma clock. It's like this, right? Rather than a pendulum clock, you can have the pendulum be above that rotates. You can rotate one way, rotate a lot one way, then rotate a lot the other way. So if you can only look at the angle of the box, not at the angle of the string.
I have a question. Definitely bring a grandfather clock and a grandfather clock.
I suspect that already in the previous comment.
See. This is related to this question. Which barrier between what's happening? So
So I guess the US is the grandfather.
Grandfather.
Okay.
No, I don't know. I thought you were making a distinction between a pendulum and a
No. This reflects the fact that my childhood, both my grandfathers passed away early. I brought it from my grandma. Okay, I corrected in the next version. Okay, so grandma or grandperson. Grandparent, thank you. Okay, so we had one of those in home. And if you just look at the angle of the bob, and you cannot tell what the angle of the spring is, you're just looking at phi mod 2 pi. If the bob has some higher symmetry, it might be like some fraction of 2 pi, as in this case. So if you look at this and measure it, you only observe the rotation of the bob, you're bound to collapse the wave function of this into a periodic structure of phi by 2 pi, right? Okay, so if you do that, then wait half a period of the oscillation and do it again and again and again. But just collapse the system reinforcedly into this periodic structure in phi. Then I have that insight, I realized, okay, I'm not going to forget this ever again. So, okay, I got it. But then you might ask, that's for fine. What about momentum? What about the angular momentum? How do I do that? Because I only have my eyes to look where the ball is. No problem. Oh yeah, there was an animation that show you. It's not that important. Yeah. So the point is, every half of never mind. So what about momentum stabilizer? So for momentum stabilizer, we want to have a periodic structure in momentum, angular momentum in this case. But we cannot observe Q. We're not measuring the speed of the bob at any point. But no worries. You just key back to physics 1 or like some analytical mechanics course, and you realize that in the harmonic oscillator, momentum and location switch every quarter period. So if you wait the quarter period, whatever structure you think you might have in momentum will switch into the same structure in location, because the phase space just rotates in the harmonic oscillator. That's why harmonic oscillators are magical. So here's the equations of motion for the harmonic oscillator, right? d phi dt is momentum over mass. Q dt is the force, spring constant times displacement. But this is just describing a circular motion in the phi q space. So if we wait t over 4, and again measure phi, we will just reinforce the structure, the same periodic structure in the q axis, with just a quarter period before. Okay, so it sounds good, but there's a constraint. So we have a particular periodicity in phi, which is 2 pi periodicity. Now the periodicity in Q, I don't know, like the only thing that I can guarantee that in the phase space of the oscillator, we will have ellipses. But the aspect ratio of the ellipse is up to the system, basically determined by the mass, the moment of inertia, and the spring constant. So if you want the periodic structure and momentum to match a particular period, you need to put a constraint on it. And in this case, the constraint is the following. So if I just look at the Fourier transform of this, then Q is like the phase times k over omega. And then I take this and stick it into the Fourier transform of phi. And, oh, sorry. Yeah, so if I take this from here and I stick it over here and I want to get the same periodicity, what I end up with, so the operator in the second stabilizer was 4 pi q. Let me stick in the h bar because now it becomes important. Momentum location have an h bar in the computation relation. I stick q from here, I get 5, so times some stuff. I want that stuff to be 1. So the periodicity momentum will correspond to the periodicity that my eyes can see in the bottom of the grandparent clock before. That gives you the following condition: 1 over square root of the moment of inertia that's being constant is 4 pi over h bar. That's what quantum mechanics does. In order to play this game, you need to adjust things to h bar. So far, how does it look? Any questions? Yeah.
So I thought the point of the stabilizer is you don't have to disrupt the state, but if you're continuously collapsing the wave function, how is that not disrupting the state?
Yeah, so this is not the end of the story. This is the beginning. But this was my intuition of, gee, how can we physically enforce these abstract stabilizers? What are they? And in this picture, you can see what they are. So basically, you looking at the bottom of a torsional oscillator. And now we can take this insight and make it into a stabilizing circuit that measures responsively. So if you do this with the T over 4 periodicity, you'll measure the system, you collapse it into something that looks like a GKP state. It's not necessarily the GKP state. It's space, you have no idea what the thing is, you need to work on it. But so far the intuition. Other questions? All right. So what's the circuit version of this? So instead of a circular, so a torsional oscillator or grandfather clock, we could do this electrically. So an oscillator electricity also is described by a phase and associated momentum, which is the charge in the circuit, just an LC oscillator. So L, an inductor, has this rule. Again, physics 1, I'm telling you, this is really simple. Voltage is L di dt. You can write this in terms of phase. You can integrate with time. So actually, this is the one thing that's not trivial here. This is Josephson relation, right? Voltage is the derivative of the phase with respect to time times h bar over 2e. That's the Josephson relation between the phase of a superconductor and the voltage on the spot where the phase is there. Now, there's no superconductor here yet, but you can describe any electrical circuit using this kind of construction. So if you write it like this, you can change this around to say that the current, you integrate this by time, the current is the phase over the inductance. Okay? It's like the spring constant. Inductor is the spring constant. What about a capacitor? Capacitor is even nicer to us. So Q over C is the voltage. We use Josephson relation. We put the phase derivative to the voltage, and we just change things around. So the phase time derivative is Q over C. That's like, so this is like the velocity, this is like the momentum, C is like an S. Then LC oscillator, nothing too extreme. The stabilizers, e to the I phi out of the box, 4 pi Q. Now Q is really a charge, so we divide by 2e. And the commutation relation is just 2ei. That's how we define Q. Before we define it as a number, now we define it with the charge corresponding to superconductor. There's another condition. Remember, there's a condition of the mass, moment of inertia, and the spring constant to allow you to see the Q variable with the same periodicity as the phase. So that translates, you don't have to necessarily follow this, but that translates to the following thing. So L over C, inductance over capacitance, that's a resistance, right? That's an impedance. And the rule that we had before, if you follow it, as in the previous page, translates to square root of L over C needs to be twice the quantum resistance of the superconductor, twice h over 3 squared, so 12 kilohms. That's the constraint that we have in this circuit. If we have this circuit, then with this constraint, then it obeys the necessary conditions of what we had before for a GKP supporting oscillator. But we still need to measure. How do we look at the phase
Why doesn't it have to be a 12 kilometer?
So there's an integer, you can do integer times that. But the reason is that so you want the periodic structure in momentum and the periodic structure in space. So in phase. Right? So let me do this here. Oops.
Right, so
I guess I just meant electromagnetism is scale invariant, so I should be able to do this for people.
So the thing that's crucial is that I do have a device that measures the phase of modulo 2 pi. So I'll show it in a second, right? We have the Josephson junction. So this 2 pi plays a very strong role in the story. Now,
I see you're making some comment that if I don't allow some impedance transformation, it might not stay.
Yeah, let me make sure. So I want the periodic structure in pi, but the GKP code requires also a periodic structure in Q, and a wave function that's periodic in both.
I mean, if you have periodic in phi, it's periodic in Q as well, right?
Yeah.
But the right period field.
But it might be no, it might be a single, sorry. What?
I thought you said you wanted periods.
I do want the periods math. So if you like edges of the Billion zone periodicity, what he's thinking of. I think there's an issue of you want something that's like outside the Billion. So it's a non-trivial statement. If you're periodic in X, sure, I mean you're periodic in you have a Fourier transform. That periodic Fourier transform would be periodic because of the periodicity in the system. Right? But you want to have a periodicity that's a smaller wave number to make this qubit work. If you don't want to trivial periodicity. So what I want is a periodic structure in Q that's non-trivial relative to the periodic structure in phi, and the oscillator will turn it around phi, right? And I have, because of the two stabilizers having very specific coefficients in the exponent, I want these points to lie at 2 pi periodicity in phi space. There's a constraint between like making the scale here and the scale of phi the same. So John was saying that the electromagnetism is scale invariant, but you have capacitance that varies from circuit to circuit. And you can think of the charge, the scaling with capacitance to give you voltage. So you have to have a very specific capacitance to give you the right voltage periodicity. Better? So it's this transformation that requires that.
Just saying this 4 pi over each bar is constant. M and spring constant, those are some, that's where we value this.
Yeah, exactly.
And that's why we said that.
Yeah, exactly. So as phi and q gets translated to each other in this rotational phase space, you want the LFs to actually be a circle. Variables. That's what's required to make it so. Other questions so far? Okay, so now there's the question of what do we do to look at this oscillator?
And look every T over 4 or
yes.
However, whichever period.
Exactly. And then the suggestion would be just connect it to a Josephson junction at some periodicity in time. And the Josephson junction has the potential that has this valleys, a 2 pi periodic location in phi, phi equals 0 and 2 pi n. Do it every quarter period. And that will collapse the system into a GKP-like code. So, okay, several things to say. First problem, you can make cetaceans, you can make clock errors. This is not very robust. It's a very highly non-equilibrium thing. You need to spike up the connection to the Josephson junction at a very specific periodicity. But still, kind of like a different approach, getting a GKP code than what was done before. And then once I understood that, I started looking at the literature, and I found this amazing paper from Jonathan Conrad from Berlin in 2020. And I have to say, I could not read anything in the paper. It was written through like strict quantum information lingo, but I saw the circuit in there. So I figured he's doing what I thought about. Single authored paper, and then Jonathan was just like a first year or second year grad student, so kudos to him. And the same idea occurred to Arne Grimsmo and clinical mantra, who was a postdoc who was working for a while on Fouquet things, and they suggested this would be like a Fouquet way of stabilizing GKP codes. If you look at this is a periodic, this gives rise to a periodic Hamiltonian. You can ask what are the Fouquet eigenstates of this periodic Hamiltonian, and sure enough, the GKP code words are eigenstates of the Fouquet evolution. And Arne and company suggested how you can ramp up the Hamiltonian to actually adiabatic to prepare the GKP code. So I thought, yeah, this is quite nice. What can I do? So the suggestion would be, let's make it better. So this has issues with non-equilibrium, with clock errors. Let's make it dissipatively stabilizing. How do you do that? Oh, you add dissipation. Just add a resistor parallel to the Josephson junction. I thought, gee, that would actually create a circuit that wants to flow into the GKP code roads. And that's where we started to work in earnest. So far, I was just describing to you a train of thought in the coffee shop at Caltech. How long were you at the coffee shop? I'm there all the time. You'll ask students, they'll tell you that if they want to find me, then they have to find me there. But it's an inspiring place.
So you're saying it's like a passive memory in some sense, you're going to make it into that, right?
Yes, exactly. So how do we make it better with dissipation? So look at the circuit. So Josephson junction gives you this periodic potential structure. Until now, it was something in our minds. We wanted to have the wave function as if it's an eigenstate of circuit. But now we produce it. We give access to this LC resonator, this Josephson. But now we say, well, the system, as we turn on the switch, can have its phi, so it's like measuring the phi. It can be at 0, but it can be at like 30 degrees, 175 degrees, 3,502 degrees. I don't know. And but if it's there, it's at some random angle, let's say here, the Josephson junction will try to produce a current associated with the sign of the angle, because the Josephson current is the Josephson energy times the sinusoidal of the angle. And where is that current going to come from? Sure, it can come from the circuit, but if the resistor is sufficiently small, that current would actually be pulled from the resistor. If the current is pulled from the resistor, there will be a voltage in this line over here. Ignore the capacitance for a second. There's going to be a voltage over here. And what is this voltage going to be? It's going to be the current times the resistance, but with a minus sign. Right? For a current to flow like this, that means that the phase over here is positive relative to 0. But it also means that the voltage over here is lower than the voltage here. Which means that here we have a negative voltage, negative phi dot, proportional to sine phi, the stable solution at the bottom of the velocity. Now the capacitance is here to satisfy our experimental colleagues. That's Thank you. See, it works. I noticed that it works. But this is a IDA.
So for the theoretical colleagues,
no,
you have a driven dissipative system with two steady states.
Yeah, exactly. Actually, you have many steady states. In the sense that any well will be a steady state. Well, any superposition will be a steady state. So we need to work a little harder, but not much harder. Yeah, but yes. So if this is the prelude to the next slide. But how about this? So this is the core of the idea. Look at the circuit. Now you can understand what's in it and why it's supposed to work. If the phase is not in one of the valleys, as we turn on the switch, the phase we want to fall down classically to the bottom of the valley. You can do it in any valley independently. And if we do it every quarter period, in principle, we should stabilize at the GKP. Does that make sense? Yeah.
If the current generated through the resistor is negative, but the Josephson junction is already doing a positive current, won't those two contradict each other?
So yeah, yes, but I think this circuit, as long as the resistance is sufficiently small, it won't happen. So if you write an equation, you can get yourself confused because it's a complicated circuit. But just think of the Josephson junction as a pump for current. So I always tell my students to put ground in every circuit they draw, and I messed up here. So put the ground over here. So 0 voltage, 0 phase. The Josephson junction, the Josephson junction immediately meets the phase over here and produces a current accordingly. Now the system can adjust to ask, like, you're pumping water. It's like your pipelines will determine where the water is coming from. So if this pipe is sufficiently broad, that will be where the water is coming from. But correspondingly, the pressure will drop. That's the hydrodynamic analogy for this. But is it helpful? I don't know. Like hydrodynamic analogy, sometimes you get to the review in the end, like it's confusing, not really helpful. Okay.
So if we had the other resistor that's missing, right? Like the one that's the parallel with the L and C, there's another small resistor there, right? Then of course we get a 0.
Yes, so that resistor has to be, so that's like a Q factor for the LC.
Yeah.
So the Q factor for this has to be in excess of 100 or so. So this would be there, you can make circuits better than Q factor. So we check that.
Your grandmother clock would like do that. Can you give me a memory? That'd be great.
That again, this is a different conversation. Yeah. So yeah, that restriction is not very large.
In fact, if you use a pendulum clock with a stiff pendulum, that has the same Hamiltonian as Josephson junction. So you end up doing pendulums all the way.
Yes. Now we're going mechanical. So okay. The Josephson junction is quite hard.
I mean, I was sure. So you have some regular stiff pendulum that can go all the way around.
Yeah,
that's the same.
Yeah,
that's the same.
Yeah, I start with the mechanical analog, so you can do it mechanically.
That would be a quantum branch channel.
That would be like connecting frontier research to contract. Yes. Yeah, but any concerns apart from that, resistor? I assume that after the talk you'll tell me all the ways in which it's not working. But...
It's also we talk about one boson that by still thinking about some kind of, can I talk about a phase given this
Yeah.
And it's in fact the function parameter space having these steady states.
Yeah. So for those of you who like this kind of thing, so this is kind of like a caldera negative phase, where the dissipation stabilizes the phase. The phase coherent superconducting state. It's not a caldera lattice, but it's in the same spirit. So Frederick actually wants to look at it as a caldera lattice. All right, so but there are concerns, particularly coherence. So resistors are nasty. Resistors have a lot of electrons in them. They respond to the function of the voltage they respond to the voltage as a function of time. Each one does it independently. So in principle, electrons can remember everything that you've done to them forever. They can decohere a system very easily. And I was concerned about that. The question is whether the resistor can actually tell which value the system is in. And if the resistor can tell which value the phase is in, this is not going to work. The resistor is going to collapse to the bottom of a value, not all values. So with that in mind, let's think about the Hilbert space of this bosonic mode. So when the Josephson junction is on, you have this periodic potential. Each value is like an harmonic oscillator, which splits its Hilbert space into harmonic oscillator levels. So you can write the wave function as a tensor product of which value you're in and which state within the value you're in. And you want this tensor product to be an exact product of some wave function in terms of n times the wave function in terms of mu that's independent of which well we're in. So in all wells, it should be in the ground state. And then we'll take a superposition of that to be the delocalized QPP code. Or it will be in the second state. If it's in the second state, it should be in the second state everywhere. There should not be correlation between the excitation within the valley and which valley the oscillator is in. But the beauty of the DKP code is that in order to in order to remember the information, the system doesn't have to be in the ground state of which valley. It just has to be in some superposition of these states. And that superposition has to be the same in the other values according to which code word you want. So we want to make sure that the resistors do not destroy that. The resistors do not have access to which value this is in. And it turns out that they have a little bit of access. But so that puts a limit on the lifetime of the state. But it's okay. So that's a little bit of a high level. I won't get into that, but if you ask me in the end, then I can get into that. But there's a more grave problem. The potential that we're putting on the circuit is not just the Josephson potential, it's also the inductance. Actually, the potential looks like this: a parabola that has this. And this is a problem because that means that in each well, there's a different energy. Now, for the GKP code words, you need to have exact coherence between all the wells. The relative phase between all the wells has to be the same. It has to be one. But if that's the case, you're going to imprint a different phase in each well. And you're going to go out of the GKP protected space. We realized this, we were really panicking. And in fact, the gravity of this problem is emphasized by how many ways you can express this problem in ways that bind. So, like, for instance, annoyed by the solenoid. It's like incensed by the inductance. And you can go on. It's like coil turmoil. I bet you by the end of the day, you'll find 5 more ways to do that. This one's really, this could be a cut, right? We're clearly a coffee. I'm glad you didn't say you were clearly at the bar. Anyway, so that was great. But then we came up with a trick. We realized, yes, it's a problem. We can deal with it because that extra phase depends on where the bottom of the wells are, right? So the extra phase has a very specific shape. It's n squared times something. But that something is just time times an energy. So this is going to mess up the state. But if we wait enough time to undo this energy scale in front, then we can make this some integer times 2 pi. So you have a collapse and revival. So you reminded us of a collapse and revival like atomic systems. So if we just weight a multiple of what you see here, 1 over, which happens to be the period of the oscillator over 2 pi, then this will become 2 pi, and the phase will be 2 pi n squared, which is an integer times 2 pi. Then it will be golden. So we had a big sigh of relief on that. Now, I am always confused by why this waiting times, which only have the inductance, or the period of the oscillator. This is because of that condition. The square root of L over C is twice R cubed. So the frequency is connected somehow to this R cubed. Frequency is like 1 over square root LC. So C and L are connected to each other because of this relation. Make sense? Okay, so now we have a complete protocol. So we turn on the switch. So we start off with some random state. We turn on the switch to get stabilization. We leave the switch on to some integer times of this wait time from before. Yes, question.
That like magic cancellation that you showed before, is that how strongly does that depend on the being exactly parabolic?
Yeah, so you want the parabola to be as low as possible. as always, you want the inductance to be as big as possible. So the way that it matters is the accuracy. So if L is small, then T becomes small, and the accuracy in T has to be better. So there's again the clock. The clock is your biggest enemy, and if you have a mistiming error, then if you have a mistiming error, this is like 2 pi minus epsilon, but that epsilon gets amplified by n squared every time. So that's where the inductance comes in. The mismatch, the time mismatch sensitivity is proportional to 1 over the inductance.
But I think the question was more about like anharmonicity in the LC circuit.
Yeah. So getting things to be anharmonic is not so easy. I think.
Very super.
Yeah, so take into account that we won't be able to get many ends, like the wave function will be spread over something like 5 to 10 values. So that will get an impact to it, right?
How can I think about having a physical error versus a logical error? Setting, is that language sensible?
Yeah, the language is sensible. And so I'll show you data about like the various operators, how they behave. But roughly speaking, here it's only logical. It's only the decoherence that you're concerned about. Like it won't decay from 1 to 0, just go away. So we just looked at the T2 for this. Okay, so I'll show you the procedure again and then ask for more questions. So we turn on the switch for like the wait time times an integer. We do this collapse revival m times, depending on what the circuit wants us to do. Choose m. We turn off the switch for some integer number of periods plus a quarter. Okay, so we want to have the quarter period turn us from charge to phase, from phase to charge. And then we repeat. So it looks something like this for the switch. This would stabilize the phase, this would stabilize the charge, and so forth. So questions? So maybe for answers. So numerics, what did we do? So we simulated this using Lindblad, universal Lindblad equation approach that Mark Radner and Frederick developed. There is just a procedure that tells you what your Lindblad dissipators should be based on just the Hamiltonian of the full system. So basically a Lindblad evolution approach. We simulated the Hilbert space using this parameterization that I told you before, valleys tensored with harmonic oscillatory state inside the valley. And I'll skip to what we get. So here's an example. I think it's the important thing to say here is that we took an inductor that's like 2 microhenry. So should give people some pause, but is doable. So here's what we see. So yeah, so over here you see the wave function amplitude as a function of phase, a function of time. Okay, and here's what we do with the stabilizing circuit, plotting the two stabilizers. Okay, so on, switch is on, switch is off, switch is on, switch is off. And then we have the S phi in the dark curve, blue purple, I don't know, I'm colorblind. My kids make fun of me, sorry. I just purple and blue there. Okay, I won't get into that. Okay, so you see that the I5 very quickly shoots up what it needs to be. But the e to the IQ, it's gonna fall over the place. But then the second operation, the second time around, you start seeing the periodic structure of collapse revival in the Q. But it's actually twice the period still. And then already in the third operation, you see what you want. So the e to the I 4 pi q gives you the structure you think you have, and then you stop the switch on when it's at one. Again, dump it into the one postulated evolution as a GKT code. And here you can see the Wigner function giving you the periodic structure in momentum and phase that we're going to be for GKT code. Now, this starts in arbitrary superposition of the two GKT code words, but we can initiate in a particular state. And here's to answer Vedika's question, here's the same circuit of memory. So we can think about like SZ and SX of the state, and I think I'm missing some labels here, so bear with me. So you can have SZ, SX, SY. If you don't have stabilization, all those Pauli operators on the qubit just decay to zero. So no dissipation, they all decay to zero very quickly. How quickly? Microseconds. But if you turn on the stabilizing sequence, see they just flat. They stay the same forever. Here are the curves for the decay. So if you're looking at effectively the T2, the SX decoherent, no resistance. There's a very quick decay at the 1 microsecond scale. With the resistance, there's also a decay, but don't look at this scale. Look at this scale. This is the log plot. This is just non-log plot. This is the zero deviation goes to like 0.0008 in 1. Like after 6 microseconds, almost nothing happens. And in fact, the T2 of this is in excess of seconds in the simulation. So questions?
What are the sigma operators? Are they're in some GKT basis? Or?
Yeah, so sigma, like think about sigma x of the qubit.
Just like some displacement.
Yeah, we had a superposition of 1 plus 0. So you start with the state 1 plus 0. And you look at how that superposition decays. How so the thing is, like, you stabilize the system into the GKT code word space, right? So you always think that you're in the Hilbert space. But if you mess up, you will collapse into 0 or into 1. Moves the phase, relative phase. This shows you that the relative phase information is system in the simulation. Other questions? All right, so just so this is again for experimentalists or experts in the audience. If you want to think about like what parameter ranges we looked at, so we thought about the near future parameter range, the imaginary parameter range, and the fantasy land parameter range. And this is based on inductance. So 1 microhenry, 10 microhenry, 100 microhenry. So I think there's a rule of nature. Like any bosonic code that Alexei Kitaev is involved in requires a large inductor. Maybe I'm wrong, but that was my impression from at least based on two examples.
Is there a reason for that?
There is. I think it's related to this need of having the inductor change the Hilbert space from periodic, from compactified to non-compactified, but without being too much of the star of the evening. Without having like the parabola of energy be too steep. Like if it's steeper than, if it's so steep such that you go out of the relevant energy range within like a 2-pi displacement, the Josephson junction starts. I think that's what it is. So that puts a pretty steep constraint that inductance kind of relevant.
So I should think of the inductor here as something which is kind of like refocusing.
So I need the inductor to create this nice P to Q, Q to P transitions. It's good for me. But I don't want it to be coherent between different wells. It's like, it needs to be just right. Like it has pros and cons, and there are places where no more pros than cons. Those places require large inductors. So I think 2.5 microhenry is that I can reasonably say was achieved. Just a word of orders of magnitude. Some of you probably use SI for electromagnetism. If you do, then you know that this coefficient mu naught is 4 pi times 10 to the minus 7. And every time you write that coefficient, you struggle for a second to know what units it's in. So you think about Ampere's law and work it out, right? So let me tell you what the units are. It's Henry per meter. It is. It's Henry per meter, which says that you just take a lump of wire and ask what's the inductance of that. It's mu naught times the length times the scale of that lump of wire. And because that number is 10 to the minus 6, it's hard to make large inductors in small spaces. Anyway, so if you do that, we can think about the 1 microhenry regime. That's what we simulated pretty much. And there's the numbers here that tell you how much flux noise, charge noise you can tolerate, how much switch mistiming you can tolerate in the order of picoseconds. Maybe this could be even better. And it tells you like the times in which it will take to do certain gates. Like Hadamard gate, fractions of nanosecond. S gate, like SZ gate, fractions of nanosecond. Readout will take about 100 nanoseconds. Initialization would be long. You need to stabilize it to the right code word. Coherence time, infinite. So it's an act of stabilizing system. Yeah.
Was it at some point wasn't the coherence time related to the mistiming time sense where?
Yeah. So this is like so if you mistime, then you lose some fidelity. So yeah, so when I say this, I think this is optimized up to this, like it's a self-stabilizing circuit. But if you exceed that, you die. I think that's that.
What is threshold referring to?
Which one?
You have a table for all those.
So that's threshold. Oh, that's how much. That's the basic of the fraction of the self-correction.
I think you said the size of the behavior state. You start off with the squeeze state, or
yeah, you start off with like some. No, you start off with like something that looks like a ground state with the oscillator. Then you turn on the Josephson collapse.
but then, like if the ground state is the size of just one of those wells, it would just be.
L has to be large.
What is the gamma? When you turn on the switch, that's what providing the energy. It costs. It actually takes energy to turn on, flip the switch, right? And that's what pumps the thing up, right?
Yeah. So you put that as left below another square and on and off.
Yeah. Because right, you're putting energy into the system.
Yes.
So it has to come from someplace. In your argument, it looks like it's nowhere, but I think when you turn on that switch,
yeah,
that costs energy.
Josephson gives you energy.
No, it can't give you energy, right? Because everything you are done is conservative. So you have to provide it. And I think when you try to push that switch, that takes energy. It pushes back.
Yes.
And that's what it is.
That's right.
And I think that's basically the 2 gigahertz is sort of, I guess, how fast you're.
So 2 gigahertz, that's the strength of the resistor. That's like how much time it takes to lose energy from the circuit based on the step down.
It's kind of like a 2 photon-ish dissipation, not exactly, but
yeah. Maybe you can think about it that was
stabilized.
Yeah. So just the last just couple of minutes, let me just flash how gates work with this. And we can discuss the parameters later. Okay, so gates. Hadamard gate. Hadamard gate, you take 1 to 0 plus 1 and 0 to 0 minus 1 for the opposite. Easy. So 0 means that we're in like 4 pi times n. Those are the values we're in. Now, if you do a Fourier transform for this, you get sum of delta functions with m times e, giving you the q. Now you wait a quarter period, and you look at what this is, you convert it to phi, and you get the delta function for phi in every well, 2 pi n. That's like the odd well plus the even wells, that's 0 plus 1. If you start with 4 pi plus 2 pi, and you take the Fourier transform of this, the 2 pi gives you an extra -1 in the Fourier transform for odd q's. That's what's the animation doing? So if you take the Fourier transform, don't follow too closely, it'll take too long. You end up with 1, which is delta of phi minus 2 pi m times -1 to the m. That's like the odd superposition of the 0 and 1. So what does it mean? Hadamard is just an evolution by quarter period. So you just change in your record keeping what the state is. Before we took it every t over r, over t over 2. Then you do a skip. It's like doing a Hadamard in the gate. And the animation that keeps running is just trying to show you. You take the phi into q, take the phi into q. You do a new Fourier transform. That's the gate.
And the gate time you showed in the previous table was just a weekly version.
Quarter period. Gigahertz circuit. So the higher the inductance, the lower the frequency. So that's the easiest. Very natural. SZ. Use the collapse revival. Instead of doing a wait time, it gives you a 2 pi. Instead of taking a wait time, it gives you 2 pi times n squared. You do pi times n squared. And then for an even, this will always be even. For an odd, it will be odd numbers of pi's. So it'll give you e to the I pi n squared minus 1 to the n. If n is even, that's like 0 code word, and odd. 1 code word, n squared is odd for any odd n. Okay, so we wait instead of t over 2 pi, we wait t over 4 pi. And then readout. Readout is tricky. Readout is the neatest, maybe. So here's one way of doing readout in this geometry. So if you take the wave function, follow it in time, as we have the stabilizing circuit on, and you look at the wave function as a function of phase, sorry, as a function of charge, like it's the transform of the wave function, a function of charge, it's a function of time. Then okay, so you have the initial GPP state, periodic structure, the period E. But then, because of this n squared times time, the phase, shouldn't say dephasing, extra phase in every well, that Fourier transform changes. You go out of the GPP state. And you get these other sets of peaks that keep changing. They keep changing kind of like, I don't know if you had the experience of driving, oh yeah, of course, you're in the Bay Area, driving next to a vineyard. Right, so every time you go a little bit, the vineyard seems to rearrange into a different crystal structure. That's essentially what's going on here. So you see that there's a focusing and refocusing. Now, if you stop, if you're looking at the stabilizer, S2, which is the charge stabilizer, at, I think, TW, sorry, at TW over 2, at the wait time over 2. I think it's over here. You see a refocusing into a set of states that's different, starting at 0, but starting at the 1 logical qubit. I know this is going fast, but here's the upshot. So if you look at the stabilizer S2, for the 0 state, it recovers to 1 in this case. So that's the code word state. Actually, for the 1 state, it goes to -1, which is outside the code space. What does it mean physically? The 1 state ends up outside the code. The stabilizer e to the sorry, I'll start the sentence again. This was in Q space. We wait a quarter period, it becomes phi space. The phi space stabilizer e to the I phi is now -1. That means that the phase sits at the top of the Josephson potential. And as you turn on the Josephson junction, that will have to collapse. As it collapses, it will give you a large current burst. With the Josephson junction, the sign is random. If you measure I squared, it'll just tell you whether you're in the 1 state or in the 0 state, where the 0 state stays at the bottom. So that will be the readout, a readout scheme. to use the time evolution when the stabilizer is on. It takes you outside the space, but in an interesting way. You wait the right amount of time for one state, go back to the closed space. For the other state, you go exactly to the polar opposite. Turn on the, you measure the current to the Josephson junction after a short wait, and you can distinguish the two states. So this is again the advantage of this particular circuit realization. So with that, maybe I'll stop. So proposal for GKT code, this is the gate drive. There are a lot of native gates. There are similar proposals that were developed parallel to us, but published, of course, a few months before us. So we are Human Group, Mark, were had a very similar proposal using frequency combs. And I mentioned the other work from Arna and Jonathan before. Future work, 2 qubit gates and D gates. So D gates actually I can give you the gossip that with some extra Josephson junction structure connecting to the inductor at strategic locations, you can use the 5 to the 4th piece to do a D gate. So if you're interested, I can tell you about it later. Well, I'll stop there. Thank you so much.
So we have time for a couple of questions. This is our tradition. The first one is has to come from.
I have a question regarding to like the ideal switch. So in like analog classical electronics, I think like most switches are actually pretty terrible. So how good like can people actually build like a switch and use a connecting circuit and maybe like model the ideal switch?
Yeah, so the switch here is probably the weakest thing, hopefully. So naively, we thought that the switch would be like immediate. How immediate could a switch be? Probably 10 picoseconds. Right? Like making the switch, look at an experimental wrong. We want something like 2 picoseconds. So actually, we can relax that a little bit. You can have the switch turn on. It does a reliable turn on function. But you can time it right. So that will be okay too. They want the timing to do the second. Was the key of the switch? Yeah. So we didn't think that.
It's probably a bit.
Yeah, it's probably a squid. They're asking about like the dissipation inherent in that squid. Yes. I said dissipation is not. But I guess it's from the circuit in a sensitive way. Yeah. But so I think that there's an impedance associated with the LC, which is sort of the forward T. But still, I think if you're down from that, the
key is to collaborate with data and help.
I'm aware of this. Yeah, so we didn't make off with this.
So for operation readout, we talked quite a lot about reading the current circuit. Isn't that going to generate a lot of heat or effective crosstalk inside of the circuit to itself? Do you have any idea how sensitive it is?
Yes, that readout would be destructive. Destructive. That's what I think we said. But yeah, I mean, several civilization steps will take away the energy. The original state.
What were your jump operators for your dissipation?
Sorry?
What were your jump operators for the dissipation?
Oh, yeah, there were, yeah, so that's something that we wanted to make sure that we got right, because that's the place where the resistor will really connect with us. So the formalism dictates what your operators are. They're just jump operators that decay energy in whatever way they can. Best of the eigenstates of the Hamiltonian under different Hamiltonian. And then there's the question: how do you do the trivial one? Do you look at long time, short time? But I think that's actually secondary. Now the thing is that operator has an amplitude. That amplitude has a small dependence on n. That dependence comes from the following thing.
So that's the label of the well?
The label of well. And it comes from a very simple thing. If I show you this potential, the minimum of the wells is not a 2 pi n. is shifted a little bit by 1 over L times N. And the resistor can figure it out because the current is sine phi, but then every minimum actually has a slightly different phi equilibrium. That thing puts a limit also on conductivity and etc. So that shrinks the basin of contraction. It was important for me to find out that this is the base just to example here. Qubit. Otherwise, say it's just a figment of my imagination. It's impossible to do this business. So that's where it is. Yeah.
Yeah, so should I, because you have this quadratic potential, you're not populating like an infinite set of wells. You're not really creating like an infinite GKP state here.
Yes.
So I guess both what is the like highest like effective squeezing you can actually get for this state? And then what is the, should I think about this very slow decay of coherence that you have because you're only populating a finite GKP? Or, okay, that's effectively one.
Yeah.
I see, okay.
But yeah, so the bigger the inductor, the more wells you have. So I think, I don't remember the number, it's a door of 5 to 10, I suppose. No, not super, not 0.
5 to 10 on each side.
Yeah.
Or, okay.
Now, there are some advantages to having a non-squeezed GKP when you want to do tricks for gates. So for instance, a key gate, you can use the fact that the n to the 4th modulo 16 is 1 for odd numbers and 0 for even numbers. A similar statement with mod gates. So you can use that to have some waiting times. If you have an n to the 4th potential, you can do waiting time to give you a key gate. Actually, Alexei told us that right away. He wrote the paper originally. And so here, if you can enable the 5 to the 4th good accuracy potential, then we can do a T-gate. That's what we're doing. Some positive result. But then you realize 5 to the 4th is proportional to n to the 4th. If 5 to the 6th is the correction, that's proportional to n to the 6th. So the higher the n is, the more messed up your system will be.
The smaller you want to be.
Yes, you want the n be small when you do this.
Yeah.
So that your accuracy of your circuit is not confined, but like 1 over n to the 6th.
Is there like a fundamental like relation you can write down then of like what the maximum coherence time you can have versus number of gates you can actually do that?
I don't know. Maybe. Maybe that's it's interesting. I don't know. Maybe. The question is back.
So I think a few slides ago you said you diagonalized by taking this. So a few slides ago you had the like harmonic oscillator times the valley decomposition.
Right.
But this is not technically valid unless you have like the Josephson potential is in perfect quadratic potential, like in each well.
No, it's not.
So is there going to be some corrections to it?
There are corrections of high energy. So that's the limitation of wanting to have the EJ large. So I have the 200 gigahertz.
Okay.
It's large because of that. So you want this to be such that the system is confined.
Yeah.
The low level states. It doesn't have to be harmonic. It just should be the other sites. That puts a bound on the EJ. We check based on Dave was asking about injecting energy. We check that the energy that you inject because of the non-equilibrium is lower than that height the leak.
Thanks.
I think we're running a little bit. Let's have one question. Please feel free to come forward.
Yeah, like